Hello everybody and welcome to our presentation today. My name is Daniel Mayer. I'm a senior engineer at Bosch and today I'm going to talk about adjoint-based design optimization of pollutant emissions in heat exchangers. The work shown today is a team effort by the people on the slides. So beside me there's Naiso Baisarison from Bosch Thermal Technology, Travis Kerrigan from Pointwise and Thomas Economan from the SU2 Foundation, who all contributed a lot, especially code, to this project. The motivation for this work is based in natural gas boilers that are developed and sold by Bosch. And on the left-hand side, you can see a wall-hanging appliance that is typically used in single-family homes or apartments. And our customers like especially the form factor of that appliance a lot because it's small and you can put it into a kitchen drawer, for example, and it's also very quiet. On the right-hand side, you can see a CAD model of the heat cell. And the heat cell is like the core component of that boiler that converts chemically stored energy in the fuel into heat, which is then used to heat up water for room heating or hot water supply. So let's take a look on the heat cell. Fuel and air enter that heat cell through the fuel valve and the air pipe. The gases get mixed in the mixer and then a homogeneous pre-mixed natural gas air mixture flows into the combustion chamber. On the right hand side you can see a cross section of that device. And you can see here that the gases come in from the top. They go through the flame holder, which is shown here as a solid surface, but in the appliance you would have many tiny holes in this flame holder. The gases get ignited by the ignition electrodes, and then the hot combustion gases flow through the heat exchanger and heat up the water that is running to the water channels. The combustion regime here, interesting for modelers, is a laminar premixed methane gas combustion mode. And during this combustion process, harmful pollutants like carbon monoxide and nitric oxides are formed. And it is of paramount importance in the development of those boilers to reduce those emissions because they are harmful to humans and animals. Furthermore, CO and NOx emissions are strongly dependent on the heat exchanger geometry, as you can see on the right-hand side. Here I have two examples of geometries, and they differ only slightly in the form of those cooling fins. And the difference in CO concentrations in the exhaust gas for those two heat exchangers is 47%, which is very significant. And this means that the reduction of emissions becomes a major driver for the heat exchanger design. However, the formation of CO and NOx are counteracting processes. So typically when you achieve a reduction of one of those species, the other one will be increased. And this is because CO is reduced by high temperatures and NOx is formed in very high temperatures. On top of that, there are many additional constraints in the development of these appliances. For example, we want to have a high thermal efficiency, we want to have a low pressure drop, and there are many manufacturing constraints that come on top, like material thicknesses, casting processes, and so on. And in the work that I show today, we do not look at all those manufacturing constraints, and we will just assume that we can build whatever we want to. In order to overcome these challenges, we think that adjoint optimization is a very powerful tool, and it will help us a lot in the research and development of these boilers. This brings me to the agenda of my talk today. And first I will talk about the combustion model that we use in our simulations and optimizations, which is the FLAMELET progress variable approach basically. And in order to introduce this, I will first talk a little bit about detailed chemistry modeling, and then finish this block with an overview of the tools and the workflow that we use in our simulations. I will then go on and talk a little bit about the implementation of the FLAMELET model in SU2. So first we'll look at the architecture and how it is embedded into SU2. Then I have one slide on the configuration of the model in the SU2 config file, and then I will talk a little bit about the validation of the FLAMELET model, where we compare it against detailed chemistry data. And then the last block of my presentation today is the application to an adjoint optimization process. And in this chapter I will first introduce the little test case that we use, talk a little bit about our work on geometrical deformation constraints. Furthermore, we implemented a functionality to automatically remesh the geometry after a geometry deformation. And this was done together with Pointwise, and Travis will tell you all about it. And then finally, I will finish the presentation with some optimization results and an outlook for the rest of this year. So let's talk about combustion modeling. One of the most accurate ways to describe reactive flows are detailed chemistry models. And the idea of detailed chemistry models is to transport mass fractions of species explicitly. So you will have an underlying reaction mechanism, and then for every species you will transport a balance, you will solve a balance equation here. And this is expensive because the system is coupled through the source term. So you can see here in the formulation of that source term, there's the mass fraction itself that you want to solve for. And this results typically in a stiff coupled system, which is expensive to solve. Furthermore, there are many transport quantities which are expensive to calculate because they now depend on the local mixture of the gas, and therefore you typically get large sums over a lot of species, and this makes the simulation very expensive, especially when you use large mechanisms. The mechanism that we use here is the GRI 2.11 mechanism from UC Berkeley, which contains 49 species and 277 elementary reactions. So that means for all the species you need to solve one transport equation, and then the system is coupled through those 277 elementary reactions which need to be solved in every iteration in every computational cell. And that means that the computational costs can become very challenging very easily, especially if this is applied to a large 3D geometry in an iterative design cycle. Which brings me to the FLAMELET progress variable approach, which reduces the computational requirements a lot. And the idea of this approach is to pre-compute one-dimensional flames, which are much cheaper to calculate, and use a very accurate detailed mechanism for this, and then parameterize the chemistry with a set of parameters, store everything in a lookup table, and then in the 3D simulation do not solve for the chemistry, but look everything up from the lookup table that you compiled from the 1D simulations. The parameters that we use in our case here is the progress variable, which is a measure for the progress of the combustion process. So it's 0 in the unburned gas, and it reaches some maximum value in the burned gas. It's typically a linear combination of combustion products. If you normalize it, it's 0 in an unburned region, and it goes to 1 in the burned region, and everything in between means that you are somewhere in the flame front. The enthalpy is used as a second coordinate to model heat loss effects that we encounter very much in the heat exchanger. And because the total enthalpy that we use here is not a function of the local gas composition, in our case we have two orthogonal coordinates in that space, which gives this model very nice mathematical properties. So here I show the workflow. First we solve a bunch of 1D simulations for on different enthalpy levels. And then we tabulate all those 1D solutions as functions of the progress variable and the enthalpy, put everything into a table, and then in our 3D simulation that we then run in SU2, we just transport 2 more quantities instead of the 48 transport equation that we need to solve for 49 species in a detailed chemistry simulation. And we just look up all the data that we need to close the system from the table instead of solving reaction equations. When it comes to emissions, however, we find that the mass fractions of CO and NO is very low if the cooling is very strong. So in order to account for that, we solve 2 more transport equations for those species, and we correct the source term following the work of Matthias and Heinz in their paper from 2008. And the basic idea here is shown in on this slide. So first we consider a generic reaction equation for the consumption of an emission species, and we call this reaction number C. And if this species is consumed, you will always have it as an educt here on that side, and we assume that it just reacts with one other educt to 2 products. When you look at the source term formulation in the detailed chemistry model again, you see that you have a large sum here that goes over all chemical reactions. And what we do now is we take out the contribution of reaction number C and pull it out of this sum. So we get this. That this sum goes over all reactions, but not over reaction number C. And for reaction number C, we get this expression here. So we assume that the stoichiometric coefficient here and here is 1, and then we get this term, and we see that the mass fraction of the species that we want to correct is in this term here. So now we call this contribution omega plus, and the consumption here omega minus, and then we split this in our table, and we tabulate the full positive contribution, but then for the negative contribution we tabulate this term divided by this mass fraction here that we find in the 1D simulation. And we assume that the transported mass fraction, that is the 1EM 3D here, is more accurate, so we correct the negative contribution of the source term with our local transported mass fraction. And this way we get a much more accurate emission model, because it introduces some history into the source term that we would not have if you just look up those quantities from the table. The tools that we use in these simulations are shown here. So first we perform 1D simulations with the detailed chemistry model, and we use 2 open source solvers here. We use Cantera for steady state simulations and Ember for transient flame calculations. The tabulation is done in an in-house tool, and besides Cantera and Ember, we also support FlameMaster files. FlameMaster is another 1D flame solver from academia. And then we load those tables into SU2 and run our 3D simulation in SU2 then. And instead of the 49 species, we only need to account for 4 additional species, or 4 scalars, which are the progress variable, enthalpy, mass fraction of CO and mass fraction of NO, which makes this approach much more feasible than detailed chemistry data. Okay, so let's talk about the implementation in SU2. You can access the code in the feature FLAMELET branch if you like to. So you can find it there. And you will see that the FLAMELET model is implemented as a fluid model class. And in here, the most important function is the function where we set the thermodynamic state. So most of the magic happens here. So in here, we look up all the quantities like densities, viscosities, and so on. We also calculate the source terms in here, and then they are stored locally and can be accessed with the get functions later on. The lookup table itself is based on work that was done in the group of Piero and Matteo. They provided us an early version of such a lookup table code. We rewrote it a little bit, and now you can find it in the feature FLAMELET branch. And it's very easy to use, and it's also implemented generically. So we hope that other people can pick this up also for not only for reactive flows, but also for other physics. I know that Matteo is using it for real gas models, but maybe there are also other applications for it. It's very easy to use, so there's just this constructor which only gets the file name as an argument, and it will build up the whole lookup table structure internally. You can report some information about the lookup table with the print table info function, and then we have two lookup functions. We still have the progress variable enthalpy nomenclature in here, but this is basically a two-dimensional table lookup, and you would pass in the name of the variable that you want to look up, a data pointer where the data will be stored, and then the value for the progress variable and the enthalpy. The second version here of this lookup routine is written for not only a single quantity, but for a whole bunch of quantities. And you can always use this if you want to look up more than one quantity, and it will save some computational time. So let's talk a little bit about the configuration. Everything is implemented in the incompressible solver that Tom developed. You can find his paper here. And the scalar framework can be used to transport an arbitrary number of scalars, and you specify the number by specifying their names with the scalar names flag. If you run the FLAMELET model, there's the requirement that enthalpy and progress variable must always be the first and the second transported variable in that list. And for the source terms, we specify two source term contributions for all scalars because we want to do the source term splitting. In our case, enthalpy is passive, so we do not account for radiation, which would be a negative source here or something like that. So we just specify null, which turns the enthalpy into a passive scalar here. The progress variable does not do the source term splitting, so we just have one positive contribution, and we set the negative contribution to null. And then for our two pollutants, we have two contributions for each. The names in this list must correspond to the names in the lookup table, and as I said, if you set this to null, you can model a passive scalar. If you want to visualize data that is not transported, you can add the names that you also use in your lookup table in the list lookup table names, and then those quantities will also be added to the paraview file. So for example, if you want to look at the source term of the progress variable or molecular weights or some other quantities, you can just add this here and it will be added to the paraview file and you can visualize it. And then the last thing that you need to specify is the name of the lookup table with the file name LUT flag. And with this, the configuration is complete. The model was validated against detailed chemistry data that we got by running the Chow code from Aachen. And we did this for the geometries that are shown here. So we have three different geometries. in which the distance P between the flame holder and a simplified heat exchanger is varied. So the flow comes in here from the left, the flame stabilizes on this little burner, and then there's this artificial simplified heat exchanger that we model with a constant wall temperature. And by varying this distance, we can basically vary the time of flight that a molecule experiences that comes out of the flame front and then goes into the heat exchanger. And then with the temperature of the heat exchanger, we can vary the cooling intensity on another level. The third, or the P0 geometry here, is a very extreme case where the flame hits the wall. This is something that you will not find in a Bosch product, but we wanted to use this here to break the model and find the limitations really of this model. So you run those three geometries and then a couple of different wall temperature, which gives us this set of validation data. And on this slide, I just exemplarily show the most extreme case. So this is the P0 geometry with the coldest wall temperature of 300 K. And on the right-hand side, you can see line plots of carbon monoxide plotted along those blue arrows here. And compared is the detailed chemistry data, which is shown in black, and it's compared to three different models. The most simple one is just the table lookup, which is the red line here, and we find that before, so this line corresponds to this arrow here, which is in front of the heat exchanger, and you see that here all models are fine. But then when we go into the heat exchanger, you see the discrepancies between the different models, and you see that the red line is unphysical, and neither the trend nor the magnitude is predicted accurately, especially at the end here, where we always find more or less zero for the CO emissions. The blue model shows the best agreement. However, it's also the most expensive one. And the green model shows the best accuracy and cost trade-off. And this is the model that I just presented. And this is the model that we used entirely in this work. So we applied this model to an optimization cycle to a simplified geometry again. So this is just a test case for the overall framework. Of course, there's the goal to apply this to a real product, but for now we just have this small test case here in which the fuel-air mixture comes in from the left-hand side. So it's very similar to the validation case, but a little bit different. The fuel here is pure methane, and the equivalence ratio is 0.75. The flame stabilizes on a burner here that is modeled with an isothermal wall of 450 K. The flame stabilizes, and then the heat exchanger is modeled with two like oval-shaped bodies here with a wall temperature of 400 K. And then on the right-hand side here you have an outlet, and we only simulate one symmetric half of the domain that you are seeing on this slide here. And in the optimization, we try to optimize average values on the outlet. So we try to minimize YCO and YNO and also the temperature on the outlet. Minimization of temperature is important because a lower temperature here means that we have a high thermal efficiency in the appliance. When we started to do these optimizations, we ran into the challenge that we typically get large geometry deformations. And this can result in a situation where the heat exchanger geometry intersects with the boundary of the simulation domain, which is something that cannot be handled anymore, and we need to avoid that. Furthermore, we found that the current implementation of SU2 lets you limit the deformation, but it's let's say, non-optimal, or it's very complicated to use. So we implemented a slightly easier bound for this deformation by introducing a bounding box for the deformation box. And you can control this with the FFD bounds flag here. And then you just specify the name of your box, of your FFD box that you want to bound. And then you specify 2 points which span the diagonal of that box. So in 2D, you just have those 2 red dots here that specify the bounds here. And then during the shape optimization cycle, we will check if your deformation box will be outside or inside, and then project that that deformed point that's outside of the box back onto the box. And you can maybe see here that we keep the direction of the deformation, but we just limit the magnitude of the deformation. So we do not project this just downwards, but we take the gradient of the deformation. Maybe here it's even easier to see. Another challenge that results from large mesh deformations is the fact that the computational grid is also deformed very much. And this can lead to very low quality mesh regions like shown here, but not only very close to the deformation, but it can also deform the mesh everywhere else. And in case that this deformation gets too strong, we get also unphysical results, or the simulation diverges. And in order to solve this problem, we teamed up with Pointwise and implemented an automatic remeshing feature. So when we look at our simplified adjoint optimization cycle here, we introduce one more block right after the shape deformation in which we check the mesh quality, and if it is under a certain limit, then we remesh the geometry and go with this. And otherwise, if the quality is okay, we just take it. And with this, I will pass over to Travis, who will tell you everything about the meshing process.
Thank you very much, Daniel. So as Daniel mentioned, large mesh deformations can result in low grid quality. And so what I'm going to talk about here briefly is how Pointwise was used to generate the baseline mesh, and a couple of considerations for generating that, how we identified candidates for remeshing, and actually went about the remeshing process in an automated fashion. So the first thing is the baseline mesh. The baseline grid was generated in Pointwise. It's a hybrid quad-dominant grid, as you can see here on the screen. And there are 2 things that you typically want to consider when you're making a baseline grid for design optimization, where you're going to be doing some mesh deformation. And the first thing is you want to keep the grid topology as simple as possible. The second thing you want to do is generate the highest quality grid that you can. And these 2 things together are going to give you the most flexibility and freedom in the mesh deformation, the most latitude in the change in the designs that you can have before you need to start considering doing some remeshing. So how do we identify candidates for remeshing? Well, we actually loaded every grid into Pointwise and examined the quality using a very inexpensive grid quality metric called the maximum included angle that's computed per element. And if it violated the threshold, it became a candidate for remeshing. And this is a little bit different approach than the first cycle that Daniel showed you, where you would deform a mesh and run a simulation. And if the simulation, say, diverged, that's a case where you want to further investigate and see if it's a problem with the mesh and then consider remeshing. The problem with that is it's a little too late in the process, and you could throw that particular case out and keep going, but if that was the design that provided the optimal result, then you just threw that away. And so by doing this upstream in the process, we can capture these, and yes, there may be more false positives, but the idea is that we're doing this before a simulation is actually run, saving quite a bit of time in the process. And so again, you see on the left here, we're calculating max included angle. If it's less than our threshold, which is 170 degrees, the optimization will continue to progress. If it's greater than 170 degrees, we will then consider that to be a candidate for remeshing and go about doing the remeshing process inside Pointwise. Now, the entire remeshing process was automated using our glyph scripting language and accomplished in batch mode. And the way it works is we take every SU2 deformed grid file, we import that into Pointwise along with the boundary condition information. We then examine the grid quality, and if it violates the threshold, then we go ahead and remesh it using the exact same settings and setup that were used to generate the baseline case. The boundary conditions are then automatically reapplied, and we export that grid to SU2. And on the SU2 side, it sees pretty much the exact same thing topologically. From a topology standpoint, the grid is identical and the boundary conditions are identical, and it can continue on with its process as part of the optimization loop. Now, all of this is defined inside the config file, the SU2 config file. We can enable remeshing from within that configuration file, and the provided files would be the Pointwise defaults project file, which contains all of the default settings and attributes required to generate the baseline mesh and do the remeshing, as well as the glyph script that performs the remeshing step in batch mode. So with that, I'm going to pass things back over to Daniel. Daniel?
Thank you very much, Travis. And with this, I would like to show you some results. So in total, I will show 5 optimizations that we performed with different objective weights. The first one is an optimization where we just optimize the temperature on the outlet or reduce the temperature in order to get a higher thermal efficiency. The second optimization is an optimization only for carbon monoxide. The third one is one where we only optimize NO, and then 2 more multi-objective optimizations, one combination of CO and NO, and then one optimization where we optimize all 3 objectives. On the left-hand side, you will see bar plots of the different objectives here, and they are all normalized to the original baseline geometry. So the geometry that you will that you see here on the right, the baseline, represents the 100% line in this plot. And then on the right hand side you will see the respective optimized geometries for the, and then the coloring represents the optimization targets, temperature, mass fraction of CO, and mass fraction of NO. So when we optimize just for temperature, we see that we indeed reduce the temperature. However, carbon monoxide increases and NO stays more or less constant. So the adjoint optimization finds only local minima or local optima. So this is what we get here. Maybe you can see as I go back again and forward again that the geometry is slightly thickened up, and this leads to a reduction of temperature. So the next optimization here is an optimization where we only optimize for the mass fraction of CO, and what you can see is that the shape gets moved a little bit to the outside here to give the CO a little bit more time to oxidize further. So CO is primarily generated in the flame front and then oxidized further to CO2 also in the flame front. And by moving this geometry a little bit to the outside here, this oxidization has more time to happen, and therefore the CO fraction, mass fraction, is reduced a lot. However, temperature and nitrogen oxide go up at the same time. When we optimize NO, the optimizer does exactly the opposite, so it moves the heat exchanger a little bit closer to the flame front because NO is primarily generated in regions of high temperature and long residence times. And when we look at our optimization targets, we see that indeed NO gets reduced by 20%. However, CO increases a lot, and also the thermal efficiency is worse than before. When we combine CO and NO as optimization targets, we find that we are indeed able to reduce both. So for this, the local optimum is even better for CO than the one where we optimized only for CO. And you can see that again, the geometry is a little bit further away from the flame front, which gives CO more time to react. Also, the cross-section area here is much larger than in the original geometry. So that means the gases flow a little bit slower, and you have more time in this region of high temperature to oxidize CO further to CO2, so CO goes down. And at the same time, NO gets cooled in the region where we have the most extreme temperatures here, which also leads to a reduction of NO of 20%. Now when we combine all three optimization targets, we get this geometry. And we are able to reduce all optimization targets. So the temperature is slightly lower. CO is not as great as in the last optimization run, but it's still very much reduced by 40%. And also NO drops a little bit. So that's great. And there are similar effects that I just explained. So this gives a little bit more room here for CO to oxidize. It also forms this increased cross-section area region where CO can oxidize further to CO2, while at the same time NO gets cooled a little bit on the sides here, which reduces the overall NO value. And here I present an overview of all the geometries. And although this is a very early optimization and is very far away from a real serious product, these kind of simulations can already help designers to give inspiration on how to design a heat exchanger maybe better to reduce a certain optimization target here. And with this, I come to the outlook. So for the rest of this year, we would like to implement a little bit more sophisticated geometric constraints, because when we go to 3D geometries, a box will probably not be enough, and we need more complex geometries. Then, of course, we want to apply this to a really realistic 3D geometry and really improve Bosch products with this. And for this, we also need the inclusion of conjugate heat transfer, which is already developed by some people in the SU2 community. And we want to merge those branches and then also simulate the heat transfer in the solid bodies. And then the last piece here, which is probably the biggest effort for the rest of this year, is hydrogen combustion for next generation hydrogen boilers. Now when it comes to hydrogen combustion, the fusion gets more complex, and we currently assume that we need to implement a third coordinate in our table generator, but also then in the lookup, because we want to account for local remixing of the species, and therefore we'll implement 3D tables. So thank you for joining our presentation today. I also would like to thank the authors explicitly, and of course the organizers of the SU2 conference. Hope to see you in person next time, and bye-bye.